Kepler's first law of planetary motion states that all planets move about the Sun in elliptical orbits, having the Sun as one of the foci. But what does that actually mean? Well, an ellipse is a shape that resembles a kind of squashed circle. Its foci are 2 points within the ellipse that describe its shape. For any point on the ellipse, the sum of that point's distances to the 2 foci is the same. The further apart the foci are, the more squashed the ellipse is. If the foci become so close that they are only one focus, you just have a circle. In reality, orbits are never perfectly circular, but we do know that the Sun will always be one of the foci of the elliptical path of an orbit. Knowing that the Sun is a focus of the planet's orbit can tell us a lot about the shape of that orbit. Kepler tells us that orbits are ellipses, which are like circles with some added eccentricity. But what is eccentricity? How do you figure it out? Eccentricity measures how flattened an ellipse is compared to a circle. We calculate it using this equation. So, what does that mean? Well, A is the semi-major axis, or half the distance along the long axis of the ellipse, and B is the semi-minor axis, or half the distance along the short axis of the ellipse. The equation is a way to compare these axes to describe how squashed the ellipse is. An ellipse with zero eccentricity would just be a regular old circle. As eccentricity increases, the ellipse gets flatter and flatter until it just looks like a line. An orbit with an eccentricity greater than 1 is no longer an ellipse, but a parabola if e is equal to 1, or a hyperbola if e is greater than 1. For example, the giveaway that Oumuamua, the first interstellar comet, was not from around here was that its eccentricity was 1.2. The eccentricity of Earth's orbit is only 0.0167. Kepler's third law states that the squares of the sidereal periods of revolution of the planets are directly proportional to the cubes of their mean distances from the Sun, which, what does that mean? Basically, it's saying that how long a planet takes to go around the Sun, its period, is related to the mean of its distance from the Sun. That is, the square of the period divided by the cube of the mean distance is equal to a constant. For every planet, no matter its period or distance, that constant is the same number. Kepler's second law tells us that a planet moves more slowly when it's further from the Sun. But why should that be? Well, as a planet orbits the Sun, it may not keep a constant speed, but it does maintain its angular momentum. Angular momentum is equal to the mass of the planet times the distance of the planet to the Sun times the velocity of the planet. Since the angular momentum doesn't change, when the distance increases, the velocity has to decrease. That means when the planet gets further from the Sun, it slows down. Kepler's second law deals with the speed of planets orbiting the Sun. So, does it tell us at what point the Earth is moving at top speed? The second law tells us that the Earth moves fastest when it's closest to the Sun, or at its perihelion. That happens in early January. At that point, Earth is about 92 million miles from the Sun. Meanwhile, it's at its slowest in early July, at its furthest point from the Sun, or aphelion. That greatest distance is about 95 million miles. That difference of 3 million miles might sound like a lot, but Earth's orbit is so vast that it's actually nearly circular.